Okay, so large deformations. We're kind of going to continue some of what we talked about last time, starting where we left off. But before we dive into some of the topics that I want to discuss today on how exactly do we formulate finite element methods in the context of large deformations, I did want to provide a little bit of supplementary information and kind of resources for you to peruse at your leisure. Obviously these are not required, but I will point out that I actually presented a couple of lectures in the course I taught last semester on this very subject, on large deformations. They're recorded lectures, so you can go online and find them if you like. But obviously, we're going to proceed under the assumption that you haven't had any of this prior knowledge. This is purely if you're interested in this subject, you want to get a little bit more additional context and understanding of the core details of the theory. I'd invite you to go and take a look at some of these, but purely at your discretion, whether you want to do that. Now, on the subject of where we left off last time, if you recall, we came up with this description of large deformations of a body that might undergo potentially large deformations that resulted in deformation relative to some initial undeformed configuration of a structure into some new deformed configuration, where those two configurations might be significantly different if the displacements experienced by the structure are large. And in that eventuality, we had to actually come up with two alternative descriptions of these different configurations, a deformed configuration and an undeformed configuration. And in that spirit, we also had to construct, by way of our finite element analysis, some mapping between these different configurations, these undeformed and deformed configurations. Ideally, we wanted to refer back to some kind of parametric domain if we were talking about finite elements. And we used that parametric domain when we were developing things like finite element stiffness matrices and when we had to carry out integration over the element's interior. So this parametric domain gave us a mapping between distinct points that lie in this parametric domain and corresponding points that lie in the actual physical coordinate space of the element. But now there are two different coordinate spaces we have to worry about corresponding to the element's undeformed and deformed configurations. And with each of those different configurations, we could associate some kind of isoparametric mapping or a transformation between these points in parametric space and the element's physical space, as well as a Jacobian. And the Jacobian gave us this mapping of not individual points, but rather how individual line segments might deform in being mapped from, let's say, the element's parametric coordinate domain into the element's physical coordinate domain. And lastly, we ended last lecture by supposing that if we have these three different configurations of interest, parametric domain, undeformed configuration, and deformed configuration, then rather than having to refer back to this parametric domain in a somewhat artificial way, we could actually figure out how we could transform individual line segments and describe how they deform after deformation by composing the sequence of operations that we would do and transforming these maybe line segments existing in the element's undeformed configuration through the inverse Jacobian into line segments deformed within the element's parametric domain, and then using the Jacobian associated with the deformed configuration to come up with what they look like now in this kind of deformed setting. By putting those two operations together, the inverse of the Jacobian and the Jacobian associated with the deformed configuration, we could actually form this new composed operation called the deformation gradient. And it's really nothing more than just taking those two operators, multiplying them together in a matrix-matrix multiplication sense, and then coming up with precisely this relationship. So the deformation gradient, in essence, is a way of mapping how individual line segments are deformed relative to the undeformed configuration and into corresponding deformed line segments in the element's deformed configuration. And that was necessary, I'll remind you, because ultimately we were working towards trying to develop some measure of strain. That's kind of the goal that we set out to achieve last lecture, which was to come up with some new measure of strain that took into account that not only do these line segments stretch, but they might also rotate significantly. But for the purpose of describing strain, we really wanted to get rid of any possible rotation that the material might experience and come up with a measure of strain that is totally independent of the amount of rotation that might be experienced by any individual material point. Okay, so a long-winded kind of catch up from where we left off last time. And I wanted to build off of this notion of the deformation gradient by also supposing that if we had some way of measuring not just the length of individual line segments, but also small units of volume, then this deformation gradient also serves another function. Not only can we relate how do individual line segments get stretched out, but we can also measure how do individual units of volume get deformed in terms of how much area they encompass in 2 dimensions or how much volume they enclose in 3 dimensions. So if we happen to know that there's some unit of volume, which I'll call D capital V, so some small differential chunk of volume in the element's undeformed configuration, it'll look different. Certainly after I deform this chunk of volume, it'll look like maybe it's skewed or stretched out a little bit, and it'll have a slightly different volume, which I'll call D lowercase v, indicating the small differential unit of volume, what it would look like in the element's deformed configuration. But otherwise, apart from being deformed and distorted potentially, these units of volume nonetheless enclose essentially the same material points, but, they've just been deformed under this kind of deformation. Now, if we wanted to measure what's the relative change in volume, comparing this initial volume, D capital V, to the final deformed volume, D lowercase v, then it turns out to do that, all we have to do is take their ratio, or in other words, take D lowercase v divide by D uppercase v. And we find that actually that ratio is associated directly with the determinant of this deformation gradient quantity that we've constructed. And there's a few different ways that you can demonstrate that that is true. And one way to demonstrate that is to actually use our Jacobian mapping in the way that we described how individual units of volume are mapped from the element's parametric domain into their corresponding physical domains. And in that setting, we used the determinant of the Jacobian to come up with that kind of volumetric scaling of small units of volume and how they are related to units of volume in the element's deformed or physical coordinates. We could do a similar sequence of transformations, not in terms of transforming line segments, but now in terms of transforming units of volume. And we could verify that indeed, this small unit of volume would be mapped into this corresponding unit of volume in the element's parametric domain, which again can be mapped using the determinant of the Jacobian into the final kind of unit of volume in the element's deformed configuration. So a few different ways to show the same thing, but in general, this measure of relative volume change, the determinant of the deformation gradient, F, is sometimes also denoted with this lowercase symbol j. Actually, it's uppercase j, but non-boldface. Now, this can get a little bit confusing because I've already defined j as the Jacobian here, so we're kind of duplicating symbols, but you just have to hang with me here. Again, this is part of the idiosyncrasies of working with all these, limiting notations in this domain. So j could mean Jacobian. I try to distinguish that partially through these colors and also through the fact that these symbols are boldface. Lowercase, or this kind of like non-boldface j, just bear that in mind. It's referring to this kind of volume scaling associated with the determinant of the deformation gradient. Okay. Now, one thing that's kind of interesting that we can use this volume scaling term for is for the purpose of evaluating integrals. Now, if you remember when we posed integrals for the purpose of computing weak form integrals to evaluate what's the internal nodal forces or what's the stiffness matrix, we had to carry out these integrals, and typically they were integrals that were supposed to be evaluated over the element's physical coordinate space. Now, using a change of variables, we could transform those integrals over an equivalent domain to do all the integration relative to the element's parametric coordinate system. But it turns out I could instead choose to use this same kind of change of variables concept to pose integration over the element's undeformed domain and basically convert any integrals posed in this format into equivalent integrals actually taken over the element's final deformed configuration. So simply by using this relationship, by saying that small units of deformed volume are related to units of undeformed volume just by scaling them by this kind of volume scaling J, the determinant of the deformation gradient. So anywhere that I have this J times D capital V, I can just replace that directly with D lowercase v, and effectively I've transformed my integral into an equivalent integral now over the element's deformed configuration. So kind of interesting. We can now do integration over, any of these three different configurations, the element's parametric domain, its, actual initial undeformed configuration, or its deformed configuration, just through this kind of change of variables concept. So that'll be useful in a moment. We'll get there in terms of illustrating the utility of that. But I want to now come back to the subject of the deformation gradient. Now, again, as I briefly mentioned before, the deformation gradient provides us some way of mapping individual line segments, usually represented as vectors, into corresponding deformed line segments, also represented as vectors. And the deformation gradient will operate on vectors with differing initial orientations in such a fashion that, let's say for this first vector, dx1, it will be deformed and transformed into this new vector, d lowercase x1, through this relationship. So some small vector dx through a matrix vector multiplication with the deformation gradient gives me a new vector that now has a new orientation. It might have rotated a little bit, and it might have also stretched out a little bit in the case of dx1. dx2, similarly, we can kind of go through the same transformation, but we find that, it'll be rotated, but it might not necessarily stretch by the same amount. Maybe it'll shrink a little bit. And in general, this mapping might also involve some kind of skewing between these two vectors, so they don't need to necessarily remain perfectly, perpendicular to each other after deformation. And in fact, if they do exhibit some kind of skewing between them, then that's kind of indicative of shearing deformations. So all of that is possible just expressed through this deformation gradient. So why do we care about all this? Again, because we'd like to come up with some description of strain that is invariant to the rotational portion of this deformation. However, obviously, we haven't really gotten rid of the rotation if we try to characterize deformations purely through this deformation gradient quantity, right? We have stretching going on, but there's also rotation. So how do we get rid of the rotation? Ultimately, what we'd like to do is to extract out the rotational part of this deformation and just get rid of it. Just, throw it away and then just keep only the pure stretching part of this deformation gradient that characterizes just the stretching along the individual axes of each of these two vectors. So in some sense, that will give us a description of deformation that is sort of attached to the frame of reference of the material itself. It's kind of like if we were to attach a strain gauge to this small chunk of material, and if we were to measure what's the strain, let's say along this axial direction, then that measurement of strain will always be measuring strain relative to some small scratch or line segment drawn on the material. And that'll be true regardless of whether this material is spinning. It'll always be measuring kind of the strain along this direction, even if that kind of direction happens to be rotating along with the frame of the material. So how exactly do we get rid of that rotational part? Well, to do that, we actually have to introduce another decomposition in the context of matrices. So if you have some experience in linear algebra, this might be a familiar concept to you that you've seen before. If not, then really the primary way that I'll try to describe this is by supposing that we have this mapping, right? We have this deformation gradient that takes us from this kind of undeformed configuration into this corresponding deformed configuration. And we do that through this just single operator F. Now, imagine a fictitious scenario in which we actually constructed another intermediate configuration that has, again, no kind of physical intuition behind it other than it's just defined for the sake of convenience, in much the same way that the element's parametric domain is kind of this fictitiously defined third configuration that we might consider. And we can actually suppose that if we're going to choose to decompose this deformation experienced by each of these different line segments, then one way we could do that is to suppose that maybe we can perform this sequence of operations to deform these line segments in a kind of two-step fashion. And we'll do that maybe first by just purely stretching each of these different vectors by some stretching matrix, kind of like the deformation gradient, but which completely excludes any rotation at all. So this kind of stretching matrix, denoted by capital U, basically is very much like the deformation gradient in the sense that it also operates on individual vectors, but it introduces no rotation. So rather than rotating and stretching these vectors, it just stretches them but maintains their relatively original orientations. And then subsequently, after we've done this stretching operation, we can come back and apply a second kind of deformation-related operation, this time in the format of a pure rotation matrix. And you can come up with descriptions of pure rotations in the format of matrices. Maybe you've kind of seen these before. But the main idea here is we can decompose this whole sequence of operations that, first stretching and then rotation in this fashion by describing the deformation gradient as just the multiplicative composition of those two matrices put together. So in order to ensure that the order of operations is preserved, we actually have to put R and then U, and that makes sure that when we took some kind of matrix vector multiplication of a vector multiplied against the deformation gradient, that it would first carry out the stretching operation on that vector and then apply the rotation. So being careful about the order in which those two things are carried out. Okay, so this particular decomposition of a matrix is sometimes called the polar decomposition. And really it characterizes exactly this idea that we can take a matrix characterizing some deformation gradient, let's say, which has some physical interpretation of how it transforms line segments, and we can decompose it into, a pure stretching part and a pure rotation part. Now, what's interesting about this is, let's say we wanted to just extract out this, pure stretching part of the deformation gradient. Ideally, that's the part that we should use when we're coming up with some description of strain. We'd want to throw away, in other words, this kind of part that depends on the rotation. But to do that, it's actually somewhat difficult to decompose a matrix in this format. There's specialized algorithms that you can use to try to actually decompose a deformation gradient into an R and a U matrix. But actually, it's actually a lot easier to do a different computation that involves just taking the deformation gradient and then actually computing F transpose times itself. And in doing so, if you assume that F can be decomposed precisely in this polar decomposition form, then taking F transpose times itself is kind of equivalent to then taking U times R transpose R times U again. And what's fascinating about this particular manipulation is that if we note that this rotation matrix, if it is indeed a proper pure rotation matrix, then it turns out there's some identities where you can show that any rotation matrix satisfies the identity that the transpose of that rotation matrix times itself gives us just the identity matrix. And if that's true, then basically it means that taking F transpose F gives us U R transpose R, which is itself just the identity. So we can kind of like say, oh, we'll plug in the identity, and effectively it just kind of goes away. And all we're left with is U squared. Now, an important observation about this is that effectively this pure stretching matrix, the capital U, if it is a pure stretching matrix, it actually has to be representable in terms of a symmetric matrix. So that's kind of nice because there's some properties that will come about from precisely that kind of finding. Certainly, we have a lot of symmetric matrices that we've worked with. The small strain tensor was effectively a symmetric matrix. And you can kind of think of the fact that we've taken the strain tensor as being the symmetric part of the displacement gradient. The reason why it's the symmetric part of the displacement gradient has to do with the fact that we were trying to get rid of the rotation that's characterized by the displacement gradient. In general, the displacement gradient might have a part which is symmetric, and that's now notionally the part that characterizes strain, but it also has a non-symmetric part. In some sense, you could think of that as being an anti-symmetric part of this kind of portion of the deformation that characterizes like some rotation or some kind of spin, in other words. And really, to get rid of this, we had to say, well, only consider the symmetric part of this deformation gradient, or rather this displacement gradient, to get rid of this kind of rotational part. And that's partly why we had, a form for the strain tensor that was inherently symmetric. But it turns out in a more general sense that anytime you have a stretching matrix as represented in this format, then that too is actually symmetric. So in some sense, if we're working with these symmetric matrices to describe deformations, they are inherently devoid of any kind of rotation going on. So we've done that. We finally achieved this kind of feat of trying to get rid of the rotation. And one way to do that is just by taking F transpose F to get, U, or more precisely in this context, U squared. So it's the square of this kind of stretch that's going on. But you'll see that actually it doesn't really matter if we're working with U or U squared. We can actually choose to define strain in any number of different ways. But one particular finding that's rather interesting, actually, is that if we do choose to examine this quantity, F transpose F, equivalently U squared, one thing that we can do is we can actually note that the deformation gradient, nominally we constructed it in this form and described it as the partial derivative of the final deformed coordinates of the structure, their partial derivative with respect to the initial undeformed coordinates. Through some extra manipulations, you can actually show that, if we suppose that the final coordinates of any point in the structure are actually represented as the sum of the initial coordinates of that point plus whatever displacement is experienced by that point, then equivalently we could write lowercase x equals old, initial coordinates, capital X plus U, which means that effectively we have to do these kind of two partial derivatives, first on the initial coordinates and then on the displacements. But you'll notice that, this operation basically, initial coordinates, partial derivative with respect to itself, basically, if you take the derivative of something with respect to itself, you just get one, right? Equivalently, in this context, you just get the identity tensor. And in this case, this is just the proper definition of the displacement gradient, the thing that we had previously. So another equivalent way to represent the deformation gradient, rather than in terms of composing Jacobians and all that, you could express it alternatively as just the identity tensor plus the displacement gradient. And if we do that, and we plug it into this expression for F transpose F, we get this nice expanded expression that involves the identity tensor plus, grad U plus grad U transpose, and then plus grad U transpose times grad U. Okay, well, what did we get from all this? Well, we just have to make one small manipulation to this, but I'll point out the fact that this term, grad U plus grad U transpose, isn't that nothing except the symmetric part of the displacement gradient? Times an extra factor of 2. So if we notice that, we can actually say, well, let's manipulate this just a little bit further, and suppose that we can just kind of maybe take, F transpose F, subtract off the identities to get that leading kind of identity term to go away, and then just divide by a factor of 2. And what we get out of that expression is something that looks like this. We get 1/2 grad U plus grad U transpose plus this extra term, grad U transpose dotted with itself. Now, it turns out that this particular definition, we can give it a name. This is sometimes called the Green-Lagrangian strain. And it is a particular measure of strain, which, if you were to imagine trying to define strain to be as closely related to the original description of strain that we had previously, the small strain tensor, then you can actually see that it agrees with the small strain tensor in the limit of small deformations. Now, how can that be? Certainly, we have this leading term, grad U plus grad U transpose. That's the part that is precisely, the small strain tensor. But we have this extra term, this grad U transpose dotted with itself. Effectively, this extra term introduces precisely this degree of nonlinearity in characterizing strain. But in the limit of relatively small deformations, and more specifically in the limit as you have very, very small displacements occurring in the structure. Imagine, these two terms that involve grad U transpose, these will be directly proportional to U, or kind of like the amount of displacement occurring in the structure. Whereas grad U transpose dot with itself, that will be proportional to U squared in general. So if you have some kind of leading term that depends on U, and you have this extra term that depends on U squared, imagine what happens when U, the magnitude of the displacements, gets really, really small. Certainly this leading term, U, will get small, but U squared will get even smaller. It'll go, basically to zero way, way faster than this leading term, to the extent that in the limit, as you make U smaller and smaller, it's reasonable to just neglect this extra term entirely. And all you're left with is, voila, the original strain tensor, the small strain tensor that we had before. So in effect, we've satisfied this extra condition of requiring that some new strain measure, this Green-Lagrangian strain measure, be consistent with the small strain tensor in the limit of small deformations. So we've confirmed that that's the case. It just includes this extra term that we've tacked on to the end. And equivalently, we could construct it in this format, which by construction, we noticed by virtue of this polar decomposition concept for the deformation gradient, we've noticed that in the case of potentially large deformations, where maybe F might still characterize some relatively large rotation going on, nonetheless, if we take F transpose F, then we ensure that effectively we're throwing away the portion of the deformation that contributes to rotation. So in essence, this Green-Lagrangian strain is a measure of strain that is totally insensitive to rotations. So if we're measuring Green-Lagrangian strain, even if the material is rotating significantly, well, we guarantee that we're always going to be measuring strain in a frame of reference that's kind of attached to the material and which more or less rotates along with it. So that's kind of the key benefit and the key distinction, simply by adding this extra term. You wouldn't think that that would have a significant influence, but surprisingly, it kind of gives all of these nice properties that we kind of wanted. So this is precisely the particular large strain measure that we will proceed with, but it is by no means the only one. I do want to point out that there are a plethora. In fact, there's an infinite number of possible strain measures that you could choose other than this Green-Lagrangian strain measure. I just choose this one because it's particularly simple. It's probably the simplest of the different large deformation strain measures. But again, there's all kinds of different strain measures. There's Henke strain, sometimes also called through strain, also sometimes called logarithmic strain. There's BO strain. There's all different types of large strain measures. And you could get kind of lost in the details if you were to dive into that kind of rabbit hole. So we won't go there. We're just going to say this is our chosen large deformation strain measure, the Green-Lagrangian strain. Okay, and that's large strains anyways. Now, how exactly do we use this large deformation measure of strain? And I want to point out why we pursued actually coming up with this description, this nonlinear relationship now between this new strain measure, the Green-Lagrangian strain, and the displacements in the structure. It depends on the displacements now in this nonlinear fashion because we have this extra term. Because this extra term is precisely dependent on U squared. And U squared is not a linear term. These leading terms are strictly linear because they depend strictly in a linear fashion on the displacements. But the extra term, U squared, that's nonlinear. That's precisely where we get the nonlinear dependence on displacement. So effectively, we've come up with Green-Lagrange strain. It's a nonlinear relationship between strain and displacement. But how do we use that in practice? How do we use that to actually come up with finite element equations that we can set up and solve? Well, we could kind of proceed along many different lines to actually derive our equilibrium equations and the stiffness matrix. But to me, I think probably the way that's least likely to get you into trouble as you go through those kinds of derivations is to actually take a somewhat different approach to the way that we've derived the equations of elasticity prior to now. And it's useful to rederive all the equations that we've developed up to now in this slightly new way, just to illustrate exactly how we would go about, doing this and generalize the procedure in the case of large deformations. But in essence, it boils down to this sort of multi-step procedure. Assuming you have some description of a relationship between strain and displacement, the idea is we start first by posing not some description of how forces are related to displacements, but instead we propose to measure the internal strain energy in the structure, which in essence is, we can come up with some description of what that is and express it entirely in terms of this measure of internal strain, whatever measure of strain that we've chosen. Then we can actually derive what are the resulting internal forces, kind of like the forces that should be applied at the nodes, by actually applying Castigliano's theorem. We briefly mentioned this concept in a previous lecture, very briefly, but now we're going to revisit this in order to actually come up with this relationship between displacements and forces. And it turns out that Castigliano's theorem comes up with a description for what these resulting internal forces are by actually taking the partial derivatives of this strain energy function with respect to the displacements. And through Castigliano's theorem, you can actually show that precisely that is a valid way of deriving what these kind of resulting forces are, just by taking derivatives of this strain energy function. It's kind of magical. It's somewhat limited to the context of elasticity, but that's fine for now. And then if you need to get the stiffness matrix, obviously you can take it one step further, just take the derivatives of the forces with respect to the displacements again, and then you have your stiffness matrix. So let's actually go about this. And actually, let's not start with this more complicated case of having nonlinear strains going on. I want to demonstrate the concept first going through the case of small strains. So basically rederiving the equations of finite elements, starting with this description using the small strain tensor. And again, posing some description of this totally internal strain energy through an integral over the whole volume of the structure that we're looking at, and involving this interior term, which I'll call the strain energy density. It is effectively the elastic strain energy stored in some small unit of material per unit of volume. So it has units of energy per unit of volume, and coincidentally, those units happen to coincide exactly with the units of stress. So if you're wondering what units are these, effectively they are units of stress that show up in this equation, but equivalently, that's descriptive of energy per unit volume. Kind of interesting. So this strain energy density function, there are many ways that you can go about describing it and kind of rationalizing where it comes from, but probably the simplest way to describe where strain energy density comes from is to imagine how much energy is stored in some piece of material when subjected to some amount of deformation. So imagine I had some, linear elastic material. I subject it to some amount of strain. I load it up to a particular value of strain. I'll call that epsilon bar just to distinguish from the actual axis here. And correspondingly, it gets loaded up to some value of stress. So I'll call that also sigma with a bar over it to distinguish from, the axis. So the question is, how much energy is stored per unit of volume by this material if it's subjected to this, linear elastic deformation, and if also we had kind of assumed that the slope of this curve is proportional to just the Young's modulus for a simple one-dimensional material. Now, ultimately, it's possible to show that the strain energy per unit of volume stored by this kind of chunk of material under a uniaxial state of deformation is really just proportional to the area underneath this kind of stress strain curve. So if I wanted to compute what's this area, I could just determine that by supposing it's, the area of this triangle, right? It's 1/2 the base times the height. So in other words, 1/2 sigma bar epsilon bar. But if I also happen to know that really, stress depends directly on strain, right? Through our linear elastic constitutive relationship. So technically, if I'm saying that this stress in the material depends directly on the strain of the material, then equivalently, I could replace, sigma bar with E times epsilon bar. And I could come up with something that looks more like this, E epsilon bar squared. And this is precisely the strain energy density in this one-dimensional context, as simple a way I could describe it as possible. But I want to point out that this needs to be generalized to the case of multi-axial loading and kind of like three-dimensional elasticity. It turns out the way to do that is precisely by defining our strain energy density as shown here. So it looks very much like 1/2 E times epsilon squared, except it involves kind of using this fourth rank tensor, the elasticity tensor. So it's, the small strain tensor multiplied on either side of this fourth rank tensor to give us back effectively a scalar measure of internal strain energy density. And then the rest of this is stuff you're already familiar with, our classical small strain tensor, and of course the displacement field expressed in a finite element context as an interpolated kind of field using our finite element basis functions or whatever basis functions we've chosen for this problem. Okay, so now how do we actually go about deriving what's the resulting internal forces that come about, assuming that we've posed this particular form of strain energy, assuming we've chosen this particular strain measure, and assuming we're using this kind of finite element basis to interpolate the displacements? Well, we have to take derivatives of this thing with respect to these nodal displacements. But that can get really nasty. It involves a lot of chain rule of differentiation, and the derivation gets pretty hairy. I actually prefer to approach that derivation by not taking partial derivatives of the strain energy directly, but instead to actually take its time rate or its time variation. So in that sense, I could define the time rate of change of the internal strain energy in this material as just U dot, which is equivalent to saying, assume that, the deformation of the structure is kind of negligible in this context. So we can just say, take then the time rate of the integral of, this kind of strain energy density rate. Sometimes this is called the stress power. When you take the time rate of this particular strain energy density quantity, what it gives you is effectively a measure of stress times strain rate. And again, it is effectively a measure of the rate of work being done by the material or the rate of elastic strain energy being stored by the material as it's being loaded continuously at some prescribed rate of straining. So again, assuming that we have this relationship between this kind of fourth rank tensor, the elasticity tensor, and the strain tensor, we can just make that direct substitution and say, well, stress equals, stiffness times strain, to come up with this description of stress. And I'm going to distinguish this as engineering stress from now on, because now we really have to distinguish what exactly do we mean by stress. There are multiple interpretations of what stress could really mean, and we really should be clarifying whether or not we're talking about, in this case, engineering stress in the case of small deformations versus some other measure of stress, as we'll get into momentarily. Now we can do the same kinds of things. If we have some measure of strain rate, we can express that in terms of the gradient of this kind of displacement with a time rate on it, which effectively is nothing more than the velocity field. So if you take the time rate of the displacement field, you get the velocity field. It's kind of the measurement of how fast are the displacements occurring at each of the nodes, let's say. Now, making a few substitutions, effectively saying, I have now these expressions that involve all these things that I can just kind of like plug one into the other and combine them all into this one final statement that kind of looks like this. Effectively, it says that my time rate of internal strain energy involves the summation over all the nodes in the structure of some term that appears here in the brackets and then multiplied by the individual nodal displacements, or rather the individual nodal velocities in this case. Now, in the case where you can make the statement that these individual nodal velocities are effectively arbitrary from the point of view of how we've gone about describing the time rate of this deformation process, we can kind of rationalize that the thing in brackets actually has exactly the quantities that we were looking for in the first place. Another way to look at this is to actually suppose that if we had gone about trying to describe this time rate of this internal strain energy density as effectively a chain rule differentiation of this kind of strain energy with respect to the displacements, then dotted with the time rate of the displacements, effectively what this says is that the term that pre-multiplies these kind of nodal velocities is nothing more than exactly the definition of the partial derivatives of the strain energy with respect to the individual nodal displacement. So effectively, this thing here in the curly braces, that is precisely the thing that we wanted, the partial derivative of this kind of strain energy term with respect to the displacements. And by Castigliano's theorem, we can relate exactly this quantity to the resulting internal forces that should be applied at the nodes. Or in other words, the thing that shows up due to the, F equals K times U. So remarkably, this agrees precisely with the expression which we had previously derived just by going through like classical theory of elasticity and building everything off of that. Simply by proposing that we pose this kind of potential energy function, this kind of strain energy function, and taking its derivatives with respect to the displacements, we directly derive this expression for the displacements. And we didn't really require significant knowledge of finite elements to do it, or any kind of knowledge of mechanics to do it either. We just had to know some calculus. We had to know how to take derivatives and stuff. And effectively, we arrived at this nice equation. All right, that's pretty remarkable. Sometimes people refer to this particular method of deriving the equilibrium equations as the so-called variational method. It's variational because you start from this description of a potential function or a strain energy function, and then you take its variations, or you take its time rate, for instance, and then you figure that kind of this quantity that appears, these partial derivative terms, are precisely those kind of equilibrium equations or contributions to them that you desire for the sake of enforcing, equilibrium at each of the nodes. Okay, so that's kind of an interesting aside, but effectively, we've derived our equilibrium equations, or re-derived them now in this new framework. However, that's obviously not where we're going to end it. Now we want to generalize this same procedure, but the only change we're going to make is we're going to say that we're going to still pose some kind of description of internal strain energy, but now we're going to have that strain energy depend on this new nonlinear measure of strain. So this new Green-Lagrangian strain measure is what we're going to plug into this strain energy density expression. And otherwise, we're going to relatively, just keep the same kind of elasticity parameters. So that rank 4 constitutive tensor, that's going to be the same as it was before. So we're really just kind of plugging in this new different description of strain, which involves obviously some nonlinear dependence on the displacements. But we can still describe displacements in the same way. So using some interpolated description using our finite element basis functions. Now, the actual derivation gets slightly more complicated, but only slightly. So if we take the time rate of this, strain energy potential function, now what we get is the stress power expressed in terms of, C times the Green-Lagrange strain. And we use this kind of description actually to define a new measure of stress, different from engineering stress, different from the types of stress measures we've talked about up to now. But effectively, it's just, that kind of, all the elasticity constants multiplied by this new measure of strain gives us this new different measure of stress. But it's nonetheless a measure of stress that we can work with. Sometimes people call this particular measure of stress the second Piola-Kirchhoff stress. And before you ask, yes, there is a first Piola-Kirchhoff stress, but we're not going to talk about it. You can kind of watch the videos online if you like that. All right, but otherwise, we can also take the time rate of the Green-Lagrangian strain to come up with its corresponding strain rate, expressed in terms of the time rate of the deformation gradient, which is really nothing more than effectively this gradient of the velocity field, which is described in precisely the same way as before. Now, one extra manipulation we have to do actually relates to how we describe this kind of Green-Lagrangian strain rate. It's kind of nasty. It involves, still dependence on the deformation gradient and kind of like these time rates of the deformation gradient. Now, through a slight manipulation and introducing yet another kind of term that I'll throw at you, which is sometimes called the velocity gradient, we can actually manipulate this expression into a form that looks a little bit slightly easier to swallow. Rather than this kind of funny term that's showing up here, we can actually describe it as F transpose D times F. Now, D is really nothing more than just the symmetric part of this velocity gradient. But the interpretation of D is effectively one which describes the strain rate in the material that respects the actual current deformed configuration of the structure. So it's kind of like a description of strain that is only really valid instantaneously with respect to the current deformed state of the structure. And the velocity gradient is really also kind of a description of the gradient of the velocity field, but it is only still valid with respect to the current deformed state of the structure. And to evidence that, you can notice that this description of the velocity gradient is effectively the partial derivative of the velocity field, but taken with respect to the current deformed coordinates of the structure. And again, that's kind of part of the consequence of insisting that this quantity is really a measure of the strain rate or the rate of deformation that's occurring in the material relative to the deformed state of the structure. So it's kind of like I'm describing all my deformation quantities in a rate sense relative to the current deformed state of the structure. It's kind of funny, but effectively that's what these quantities describe. Now, if you have this description of a velocity gradient and the corresponding rate of deformation tensor, if you like, you can call this the current strain rate tensors or something like that. Now we can come and put all these things together. Again, proceeding along similar lines, we have all these different relationships that we can kind of plug in to come up with this final relationship, which I'll just kind of like cut to the chase and describe. There it is. That's the final expression, effectively the internal force that we're looking for. But I do choose to make a few substitutions and modifications to make this final expression look slightly more similar to what we had before. And in particular, if you notice this description of second Piola-Kirchhoff stress, this kind of S measure of stress that depends on Green-Lagrange strain, this stress power term can actually be manipulated through a sequence of steps into a format that involves not the Green-Lagrange strain rate, but instead this rate of deformation tensor, the thing that we just defined, the symmetric part of the velocity gradient in particular. And it involves basically making some transformations and kind of manipulating this kind of into a format that involves F times F, S times F transpose. And without belaboring some of the details on this, I just want to point out that sometimes people call this whole assemblage of things 1 divided by J, the volume scaling term, times Fs, F transpose. This is sometimes called the Cauchy stress. And more specifically, it's sometimes referred to as the true stress. In effect, the true stress is truly the measure of stress that you should be using if you're trying to describe stress with respect to the current or deformed state of the structure. It is properly a measure of force per unit of area, but not just any area. It's per unit of area in the actual deformed configuration of the structure itself. So that's kind of the distinction. True stress is always measuring force per unit of currently deformed area, kind of like you would have in that necking bar type of problem. If you're measuring true stress, you're properly taking into account the amount by which the necked area of the bar is decreasing and normalizing kind of that stress measure relative to this reduced cross-sectional area. So true stress is properly the stress that we should be using in this large deformation context to describe force per unit of deformed area in the structure. And if we make that substitution and acknowledge that this is the measure of stress we should be using, that this is how it's canonically defined, it turns out that a lot of things kind of cancel out and we get a nice final expression that looks remarkably similar to what we had before. Again, you can rationalize that's precisely the, through Castigliano's theorem, this is the measure of kind of internal forces that we would like to have at the end of the day if we're solving finite element problems by assembling internal forces that depend in this now nonlinear fashion on the displacements in the structure. But I want to point out the differences here. And there are a few. So on the left, we have the case of small deformation. proceeding along the lines of re-deriving all these expressions as we had before. And on the right, we have large deformations. And they start respectively from assuming that we're using this measure of small or engineering strain, if you like, versus this large strain measure, the Green-Lagrangian strain. And really, the only very subtle distinction is that we're including this extra term here, this one small extra nonlinear term to describe strain. Now, we can then go about describing what's the corresponding measure of stress in the material. In the case of small deformations, it's this engineering measure of stress, which is just, C times epsilon, the small strain. Correspondingly, in large deformations, we have this other measure of stress, the second Kilwood-Kirchhoff stress, similarly related, linearly related to the Green-Lagrange strain. So slightly different description of stress to match this slightly different description of strain. And we could choose to not just describe everything in terms of this weird second Kilwood-Kirchhoff stress. We could, make a slight modification that involves some extra multiplications by the deformation gradient and divide through by the determinant of the deformation gradient to come up with this description of true stress. So also denoted canonically with a sigma, which is kind of why you see I wanted to distinguish that this is really not the same as this measure of stress. This is true stress. This is really more descriptive of engineering stress. And if you like, engineering stress has more of an intuition as being stress per unit of area, or rather force per unit of area, measured relative to the undeformed configuration of the structure. That's the key distinction. Okay. Now, when you come to these final expressions, you might be baffled and say, well, aren't they the same? They look identical, right? I'd have stress times, the partial derivatives of my nodal basis functions with respect to coordinates integrated over the whole volume of the structure to give me the resulting nodal forces. But the key thing I want to point out here, to the undiscerning eye, they might look the same, right? Point for point, they look the same. But the key thing that's different is this description of stress, obviously, is totally different. It depends directly on the small strain measure, whereas this description of stress, the true stress, has a bunch of extra manipulations we have to go through to get it. So that's point number one, the point of difference. The second point of difference is that these quantities, the derivative quantities of how we're taking these kind of derivatives of the shape functions, these derivatives are taken, at least in the case of small deformations, relative to the undeformed configuration of the structure. In comparison, the derivatives we take for these nodal shape functions, in the case of large deformations, they have to be taken with respect to the deformed coordinates of the structure. Very subtle distinction, but makes a huge difference. Similarly, we carry out integrals over the undeformed volume when we're doing everything in small deformations. In large deformations, integrals are carried out over the deformed configuration of the structure. So everything is with respect to the deformed configuration when we're talking about how we compute these forces in the case of large deformations, whereas in small deformations, everything is with respect to the undeformed configuration. And we kind of also implicitly are making the assumption of we're just using this kind of small strain measure. So very, very, interesting to point out these very subtle apparent distinctions between these two things. But it is important to kind of point them out that even though it looks like we get all the same things, they do differ actually quite substantially. And you don't actually notice those differences until you go and try to solve a problem and kind of see, how do they differ? You'd be surprised. There are certain problems that if you try to run them and you assume small deformations, you will get wildly inaccurate results, things that are just utterly nonsense. So truly, this description of equilibrium is much closer to reality than this description, even though this one's a lot easier to do and a lot easier to kind of like set up and solve. Ultimately, if you can afford it, large deformations really is truer to reality. And that's the way you ought to go. Now, I think that's all we have time for, so I'll let you go here. But I do want to point out that if you have an interest in kind of reconciling a lot of the terminology that I've thrown at you, these different measures of stress and different interpretations of what exactly they mean, again, I'll invite you to go maybe rewatch some of those videos that I had. I go into a little bit more detail in describing and distinguishing between what do I mean exactly by, Cauchy stress or true stress versus engineering stress, and how exactly do I describe, these different deformation states with respect to the deformed versus undeformed configuration. So if you feel like you need a little bit more to reinforce some of these ideas and you want to kind of solidify them, go ahead and check out some of these videos. I kind of go into some of the topics as kind of shown here. But in any case, that's all we have time for. We'll pick up on Monday. Otherwise, I'll see you then. Stay safe. Have a fun weekend.